Hey everyone, this is the long-awaited June 2026 Earth and Space Science Regents exam. I'm going to go through the whole thing. I'm going to go through and rank the questions on a scale of 1 to 10 on how difficult I think they are. 10 being the hardest, 1 being a joke, and this was the test that made the news. So we're going to go through it. Now, I do have to say I have taken this already, so this is not going to be like a blind sort of thing like I did with the other regents. I don't remember the questions that well, so you're going to see me go through and figure them all out as I go, and I'll rank them 1 to 10. So feel free to look in the look through and scrub through to the questions that you think you got wrong instead of watching the whole video, but this should be just used as a general study guide to see how you did, to get better, and to do really well on future ones if you have to retake it. Okay, so we're going to go ahead and start with number 1. Here we go. So base your answers to the questions 1 through 4 on the information below. We have our reference table ready to go, just in case. And this one is on an Iceland hotspot. So right away, hotspot, I'm thinking automatically to go to the pages in the reference table that have hotspots on it or plate boundaries or something to do with this. So I'm here on these pages because I know that's there. Iceland's one of the most active volcanic regions on Earth. It's a hotspot in the North Atlantic Ocean. So now, okay, ocean, now I'm thinking ocean currents. Automatically, page 20, North Atlantic Ocean, see? So these are the things that I'm thinking about as I go. Near the Regents, I can't pronounce that, Regents Ridge. The island formed by a combination of seafloor spreading and volcanism, okay? The map below shows some information about the tectonics of Iceland. Here's Iceland. I'm also thinking of where Iceland is. So I go here. I'm going to try to find Iceland anywhere I can. Right here. See Iceland labeled right there. That might be something that I need to know. And we have our zones here. And this is, if you go here, you could see there's a ridge that's going right through Iceland, and it's a divergent plate boundary. So we could see that automatically. Here, so you could see right there, and there's our arrows that are diverging, right? So we know this. Okay, let's see what the question says. Place the letters representing locations A, B, C, D in the spaces below to show the pattern in the ages of the rock from youngest to oldest. So the thing to know about this question is that you have to know that the rocks nearest the ridge are the youngest, and as you go away from the ridge, it's older. So just based on that, C is closest, so this is going to be number 1. Then B would be second, and then A would be third, and D is the furthest away. So there's my order. So it should go C, B, A, D. Okay. So I thought that question was super straightforward. I give that a 2 out of 10. I thought that was very easy. Number 2, which statement correctly compares the rate of seafloor spreading? So rate of seafloor spreading, that is located here. There's your rates. So the numbers on these pages are your rates. At the ridge in Iceland to the rate of seafloor spreading at another plate boundary. And they're going to ask me for different ones. So I know I'm on this page again. So the ridge right here is at 1.8. Okay. So Iceland's approximate rate of spreading, which is 1.8, is faster than whatever this one is. Iceland's approximate rate of spreading, which is 1.8, is slower than whatever that one is. Iceland's approximately rate of spreading, so that's 1.8, is faster than whatever that one is, and then here. So I'm writing out these numbers because then I'm going to write the other numbers, and then I'm going to reread the sentence, and I'm going to see which one's right. So now I'm going to check the Southeast Indian Ocean Ridge. So that is here. So that's looking like it's 7.4. So now I'm going to write that in for here and here. Oh, that's southeast, so you got to be careful here. Southeast, and then we have southwest. So Southwest Indian Ridge is 1.6. So now we're just going to reread those and see if we can eliminate. Iceland's approximate rate of spreading, 1.8, is faster than this one, 7.4. Nope. And then Iceland is slower than this one. Nope. So now those two are out. So now I have to check East Pacific Rise, which is... And just imagine a student going and you're going to have to try to find this East Pacific Rise right here. So this is looking between 15 and 16. And I'm just estimating right there. So we'll just call it 15.5. And then the Cocos and Nazca plate rate of spreading is right here, Cocos and Nazca. So it's 7. Okay, now we're going to read those sentences. Iceland's approximate rate is 1.8 is slower than the East Pacific rise. Yes. So that's possibly correct. Iceland's spreading rate 1.8 is faster than Cocos and Nazca, which is 7. That's wrong. So it's 2. So I think, honestly, this question is like a 3 out of 10. The only way I could see people get tripped up is be confusing Southeast and Southwest Indian Ocean, because they might be reading fast and not notice that there's a difference right there. Or if they didn't know that the page in the reference table is where you needed to go, that's a huge problem. You would never get it. But otherwise, it's really very straightforward question there. Okay. Blah, 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 blah volcano is located on the south coast of Iceland. On April 14, 2010, an explosive eruption occurred in the ice-covered crater. Okay, so we got an eruption. Okay, south coast of Iceland. The mixing of the glacial water and magma resulted in a massive ash cloud that went approximately 11 kilometers into the atmosphere. The cloud consisted of large amounts of microscopic particles and a hard volcanic rock. Okay, the map below shows some information about the movement of the ash cloud and the volcanic eruption in 2010. The key indicates the distribution of the ash cloud over time as a result of the eruption event. Okay, so we got this ash cloud here, and there's dates when the ash cloud was over certain areas, and then there's the patterns on the map. Okay. Which statement based on the evidence found in the map describes how the movement of the ash cloud influenced humans? Okay, so this is just going to we're going to read the sentence and just see if we can make sense of the map and get the answer. Okay. So number 1 says, between May 5th and May 18th, all of Iceland was most likely experiencing poor air quality. So May 5th and May 18th there. So if you look at Iceland, it's pretty bad. So May 5th and May 18th, all of Iceland was most likely experiencing poor air quality. I don't like that it says all, because there's some pattern not available there, but we might be able to say that that's right. But we're going to just see. By April 18th, the southern tip of Greenland was most likely experiencing poor air quality. So southern tip of Greenland's right there. There's nothing there. So that's not true. On April 23rd, residents within southern Europe experienced total darkness due to the ash cloud. So we would want southern Europe. So that's down here. There's no pattern there. So that's not right. And on April 15th, residents in the United Kingdom, which says it's here, experienced increased atmospheric visibility due to the ash cloud. That's definitely not going to be the case, because more ash cloud would mean decreased visibility. So that's wrong. So the best answer to this is 1. I'm not crazy about this question because you can't say all necessarily. That's like kind of an assumption, and it's not based off the patterns that are shown, in my opinion. So I give this I would say a 4 out of 10, because we eliminated 2, 3, 4 pretty easily. Honestly, that are definitely no, but I don't really like this question too much. Like, it's not great. So I would say that's not great writing, in my opinion. Unless I'm missing something, in which case tell me in the comments. Number 3. All right, managing and mitigating lava flow. So mitigating, just so you know, means like trying to prevent, to lessen how bad it is. Managing and mitigating lava flows from volcanic eruptions is a challenge due to the intense heat and fluid dynamics of lava. In Iceland, several solutions have been applied or proposed to address the impacts of lava flows. So we got possible solutions here. The table lists different methods that all require equipment. So they all require equipment to address the impact of lava flows on communities. Okay. And let's just see what the question is. Which solution would best protect an Icelandic community from a lava flow when considering constraints such as costs and equipment? So based on those 2 constraints, we want to say we don't want to spend a lot of money, so we want cheap. And constraints of equipment, saying we don't want to use equipment, or we can't use a lot of equipment. Okay. Now, my issue here is that they all require equipment. It literally says that. So why are they saying they're considering equipment as a constraint? I think that's like silly in terms of this being a question, but whatever. Okay, so we'll just say we want it to be cheap and no equipment. So here we go. Lava diversion, construct channels to redirect the lava. Look, costly. Okay, so that's automatically wrong, because we just said constraint is cost. Okay, great. Seawater cooling. Use pumps to draw seawater to spray lava to cool and harden. You need a constant water supply. The demand for energy to run multiple costly pumps. So we have a costly problem again, so that's out. Or these are at least equivalent so far. Neither of them says anything about needing a lot of equipment yet. Next one, lava flow barrier. Build barriers to dam the lava and stop its flow. Look, need machinery and equipment to build the barrier. So that's automatically going to be an issue because we don't want to use a lot of equipment. D, explosions. Detonate explosive to disrupt the lava flow and redirect its path. This could cause further damage. That could be costly, but it doesn't say costly. And loss of life, that's really bad. We don't want to kill people. Not precise, and lava could return to the original path. So this seems like a terrible idea, but this doesn't say anything about the word costly like this does. See, costly, costly. And it doesn't say the word equipment like this one does. So really, the best answer here, in my opinion, according to the question with those two constraints, is D. But obviously, we don't want to kill people. So that's not good. So this question is the worst. I already know because we had an issue with this question. This is the worst question. It's unfair. It's poorly written. It doesn't make sense. I don't know how they thought that an answer would be able to, like, there's no right answer to this question. So like for me, if it was me on the test, I would probably pick like, I don't even know what to pick because I don't want it to be costly or have a lot of equipment. And they all say that except for D, but D is killing people. So I don't know. I would be between A, B, and C. I don't think this is good because it says lava could breach the barrier. So now I'm thinking of the actual method. And then again, lava may breach here. So maybe that's not great. Redirect flows instead of stopping the flows. This one says it needs a lot of water, but it has a demand for energy. But this one seems like it's the best option between A, B, and C. So I would get that wrong, just so you know. So they said that the answer should be C. I cannot explain this question, truly. So I would say this is not possible. That's my opinion. That's all I'm going to say about it. Terrible. Going on. Base your answers to question 5 through 8 on the information below and your knowledge of Earth and space sciences. By the way, just to go back to this question, we had 6 Earth science teachers do this question, and mostly everyone got a different answer, and all justifiably so. So they all explained why their answer was right or why the other ones were wrong, and were able to do that in a way. So if they want to make a question like this, you would have to make it a short answer question and have multiple answers. Be like, okay, if a student picks A, they have to like back themselves up with evidence as to why they think the answer is A. You can't say this is an ultimatum multiple choice correct answer. It's not right. Okay. Stars and stellar evolution. Here we go. The Andromeda constellation contains several stars, including 3 of the brightest stars in the sky. Olmec, Merak, and Alpharites. Sounds like a pasta dish. Olmec is a multiple star system located 350 light years from the Earth. Okay, that's pretty far. A light year is defined as the distance that light travels in 1 year, which is 6 trillion miles, or that. The Olmec system is the 3rd brightest object in the constellation. So Olmec is 3rd brightest. Merak is a red giant star. So now I'm automatically thinking life cycle of a star. So I'm on these pages. I'm like, here, look, red giants, things like that. It could be the HR diagram. I might need this, not sure, but I'm like, that's in my head right now. And it's approximately, so 200 light years from Earth, but it's 2,000 times brighter than the sun. And then Alpharites is a subgiant star located 97 light years from Earth. Now, I'm not going to highlight the light years anymore because I know that that's not on the reference table, but this one says 350, 200. Actually, I'll do it because they're, whatever, we'll see. From Earth, and it's approximately 200 times brighter than the sun. Now, they could ask, again, I did this, but I don't remember. They could ask luminosity here. So 200 times brighter, we could maybe be here, but we'll see. The Andromeda galaxy, known as M31, is also within the Andromeda constellation, and it's 2.5 million light years away from Earth. That's the Andromeda Galaxy. The Andromeda constellation is visible in both the northern and southern hemispheres of the Earth, but it's not visible at latitudes greater than 40 south. In the northern hemisphere, the constellation is best observed from August to February. Okay. In the southern hemisphere, it's only visible from October to December. And we have this thing here. So let's just kind of see what... So there's the galaxy. And then there's some stars. Okay. Which row correctly lists the factors that influence nuclear reactions in stars and lists the types of elements in the core of some of the stars named in the Andromeda constellation? Okay. So first of all, things that influence reaction in stars is going to be the star's mass. So definitely mass. So we like this. Brightness will not affect the nuclear reactions in a star, so that's out. Distance will not affect it, its nuclear reactions, and that's automatically distance wrong there. Wow, that was so easy. I didn't even have to do that part. So the only one it could be is 1. So I would say this is a 2 out of 10 question on stars. Very easy. Very easy. The model below shows information about the zodiac constellations visible from the Earth. The ecliptic is the sun's apparent path amongst the constellation as viewed from Earth. So in this picture, we have the sun here, and we have the Earth revolving around the sun. So you could see May to September to January. So that's the Earth. And they showed the arrows that the Earth's revolving around the sun. And then you have constellations in the sky that are visible. Okay. Identify the name and motion of the object shown that's responsible for the pattern of different constellations that are visible to the observer. So first of all, the name and the motion of the object shown in the model would be the Earth, because the Earth is changing its position as it revolves around the sun. And it says the constellation's visible from the Earth. And it's saying that's what's changing. So the name and description of motion is going to be Earth's revolution. You could also say like Earth's orbit around the sun, probably. Revolution around the sun. Okay. Now, the issue I have with this right away is that there's one blank and they're asking 2 different things. So I think they should have wrote like name, 1 blank, and then motion, 1 blank, and then constellation name. So there should have been 3 blanks here, first of all. Because if a student didn't put the planet name or or like the celestial object just means a space object shown in the model. So if they got the name wrong, automatically the whole question's wrong, which stinks. If they didn't write revolution or orbit, the whole question's wrong already, even if they get the next part right. So identify the name of one constellation that would most likely be highest in the night sky at the same time that the Andromeda constellation would also be visible in the night sky at midnight in January. So look, January, midnight, that's the side, so it's Gemini. So like that part was easy. This is the issue that I have. This part was kind of hard. I'm going to say this question was like a 7 out of 10. Like just because of how many parts are in it, like I thought this was kind of hard. Like I would assume a lot of kids got that wrong. Okay, going on. The graph below shows the evolution of a sun-like star. Okay. Numbers 1 through 9 represent the steps in the sequence of a star's evolution and its positions on the HR diagram. So there's our HR diagram, and I'm immediately like, boom, like right there, HR diagram. It's ready to go. Luminosity is the total amount of energy radiated by a star. Okay, we know that. And the term burning refers to fusion. Okay, and it's got its own HR diagram here. Which piece of evidence in the evolution of a sun-like star graph could be used to support the claim that nuclear fusion is the process responsible for energy generation in stars like our sun and Merak? Okay, so you can see all the numbers are labeled. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. And it looks like this is the path of a star. Okay. And it's just saying in that step, something happens. So we're just going to go through each one and see if we can eliminate. By the way, that is the ultimate strategy to this test, if you didn't figure that out yet. Based on what I'm doing, everything is how can I eliminate these answers? That's what you have to do. And that's what makes this take long. So, because it's like you're really kind of having to spend a lot of time eliminating. In step 4, Helium burns in the core, then helium burns in the shell. So let's look. Number 4. Helium core burning starts, hydrogen shell burning continues. Helium burns in the core, then helium burns in the shell. So this says hydrogen shell burning continues. So that's not right. Okay, let's keep going. In step 7, outer layers of the star are ejected and become a planetary nebula in step 8. Let's see. Look, step 7, outer layers are ejected, planetary nebula forms. That looks like it's good. From step 2 to 5, hydrogen burning changes to helium burning in the core. So let's do this again. 2, hydrogen burning. 3, hydrogen burning. 4, helium flash. Helium core burning starts. And 5, helium burning. So this is true. So now I have a problem because I have 2 that are probably going to be right. So now I got to go back after I check 4. From step 1 to 3, hydrogen core burning stops and thermal pulses begin. Okay, thermal pulses don't begin until before 7. So that can't be right. Okay, so now I'm going to go back to 2 because now I had 2. So I have 50-50. Let's go to 2. In step 7, outer layers of the star are ejected and become a planetary nebula in step 8. Outer layers ejected in step 7 and become a planetary nebula in step 8. Planetary nebula forms with central star. Okay, so the reason why I'm between the 2. So now I'm going to go back to the question, and basically it's saying which of these could be used to support the claim that nuclear fusion is the process responsible for energy generation. So unfortunately, because they're specifically asking about nuclear fusion creating energy, the best answer is hydrogen burning to helium burning. Hydrogen to helium is fusion. So 3 is going to be the best answer. Even though 2 is technically right, it doesn't actually provide evidence for supporting that claim. I hate this question. I think it's cruel. It's just, I don't know. I don't like it. So I would say this was pretty hard because it's a 50-50 here. I'm just imagining I'm a kid, right? It's a 50-50 between 2 and 3 just based on the thing. And then they had to figure out what the question was asking. So I'm going to call this like a 6 out of 10. Just because I would say it's harder than that, but you should be able to narrow down that both of those were correct, and then you would have had to figure out why one of them was right and one of them wasn't right, even though both were correct, and then you had to go back to the question and figure that out. That was the hard part. So 7-3, I don't like it. Let's do a fun game. Let's just see how many questions I don't like, just for fun. So there's 1, and then we have this one I didn't like. That's 2. And then I didn't like number 4. That's 3. I got to keep a tally. I think so. I'm at 3. 3 questions I don't like so far. Okay, let's keep going. In 1924, Hubble studied the Andromeda Galaxy along with many other galaxies and found that there's a pattern in the speeds that the galaxies are receding from the Earth. Receding means going away from. Hubble's finding had important implications for theories related to understanding the universe. The table below shows some information about galaxies, including their distances and recessional velocities, which is their speed relative to Earth. Black arrows below the spectra indicate how far the 2 darkest absorption lines have shifted in wavelength. Okay, so we're talking redshift, blue shift, things like that, how much they're shifted. So you could see approximate distance, 52 million, 60 million, a billion. So we're increasing distance, and you could see the wavelength speed is increasing. So this is just Hubble's law. So as distance increases, recessional velocity increases. So that's basically basic Hubble's law. So that's pretty simple. We should know that. So now it's going to say 4 statements about the universe labeled A, B, C, D are shown in the table. Which I'm not reading them yet. I'm just going to see what it says. Which pair of statements supports the Big Bang theory? Oh, I didn't I wrote in my predictions that there was no Big Bang on this test, so I got that right. Oh, there was a Big Bang. Okay. Which pair of statements supports the Big Bang theory based on the given astronomical evidence of the light spectra, galaxies, distance, and galaxy velocities? So we need to support the Big Bang theory. Okay. Let's see. The farther away a galaxy is from the Earth, the more light is redshifted, increasing acceleration. Yeah, that's Hubble's law. We like that one. A is good. So any of them that don't have A is wrong. I'm just going to assume that. Now I'm 50-50ing. B, the greater the distance a galaxy is, the more recessional velocities decrease. No, because it's going to increase recessional velocity. I don't have to check C. And then D, as distance of galaxies increases, the recessional velocity increases. Yeah. So this is A and D. I would say this is a 2 out of 10. This is very easy. Really easy question. Okay. 9 through 13 on the information below. So now we're in the carbon cycle. The slow carbon cycle is controlled by various geologic processes that move carbon between Earth's spheres. Carbon takes millions of years to move between the rock, soil, and ocean, so carbon cycle, okay, and the atmosphere through a series of chemical reactions, so carbon takes millions of years. Now remember, it's sped up by humans. The movement of carbon from the atmosphere into rocks begins when the carbon dioxide combines with rainwater, which is dissolution, okay, to form a weak acid, which is carbonic acid. The acid dissolves rock, releasing the ions that are carried to the ocean. Okay, we're carried to the ocean. These ions combine to form calcium carbonate. Okay, over time, this calcium carbonate builds up on the ocean floor, creating sedimentary rock. Okay, carbon dioxide can be returned to the atmosphere through plate movement and volcanic activity. Okay, complete the model by placing the correct terms from the choices below in the boxes to describe the cycle of carbon. Not all terms will be used. Okay, let's see. Okay, so first of all, right here, process that forms weak acids. That's literally right here. Look, dissolution forms a weak acid. So is that a word? Yes. So this is dissolution. So that was from the reading. And then that turns into a rock. This is a process. Rock something. And then it goes into the water. So let's see. This weak acid dissolves rock, okay, releasing ions that are carried to the ocean. So carried. So this is going to be carrying to the ocean, so that's erosion. Now, it could arguably, if you say dissolves rock, that could be chemical weathering. So I would say I'm going to put erosion there because of the carrying, and I see the arrow like it's moving into there. So I'm going to go with erosion there. Now, just so you know, they did take weathering or erosion for this box because those are both arguable. Finally, they're taking multiple answers for something. Like, they need to start doing that more because so many things are arguable on these tests. Okay. Then we got dissolved ions, sedimentation. So we're making a sedimentary rock, and we have to turn it into a rock over time. So think of acid forming weak acid into the ocean. Ions combine to form calcium carbonate. So that is going to probably be a limestone. Shale is made from like dirt particles. So limestone is going to be the answer for the rock name. Then we just need this. So this is the process. So look, the arrow's going down. This process is subduction right there. So I would say on this one, I would say this is a 5 out of 10, just because I would see a lot of students not knowing which rock to pick here, shale or limestone. But the other three should be totally doable. So that's why I'm going to call it a 5 out of 10. So I could see kids being 50-50ing on this rock, basically. Not terrible question, but not the best question either. But it's not a don't like. I'll just leave it at a 5 out of 10. Okay. The models below show some information about how silicate rocks are weathered to produce carbonate rocks that cycle carbon amongst the spheres of the Earth. And you got all this stuff. I'm not even going to bother looking at what this is yet. Okay, this is all chemical formulas and stuff. So let's just go see what it wants us to do. Oh, this is our second short answer. Describe how plate convergence cycles carbon in carbonate rocks by convection. from the lithosphere to the atmosphere. We need to cycle carbon in carbonate rocks from convection. Okay, let's look. So convection currents are down here. Melting. So look, melting of the. Okay, wait. When I think of convection, you're thinking of the loops under here in the asthenosphere. So the plates move. Convection is going to cause subduction. Okay, so here we go. The carbonate rocks that are in the rock, they're going to get subducted and they're going to melt. See, melting of the rock. And then that rock is going to rise up and then the carbon dioxide is going to go out into the atmosphere. That's the answer. We just need to make that into words. So just that is the content right there. So I would say for a kid to be able to know that, I think it's doable, but it's a little bit high level. So I'm going to say this content question is a 7 out of 10 in difficulty, and then they have to put it into a sentence that makes sense. So maybe I'll call this like a 7.5. I think that's kind of tough. So I would write something like this. I'd be like, okay, carbonate. Oh, wait. Because I have to say something about convection. So we could say convection causes carbonate rocks to subduct and melt. Then the CO2 is released through volcanic eruptions or outgassing. I would say that's a good answer. But obviously, like, that's me answering it. So if I'm a kid, I think that question's hard. I like the question, though. I do have to say, I do like that one. I think it's a good question. Hard, but good. Okay, which statement identifies how the silicate rocks that have been chemically changed by water produce carbonate rocks in Earth's ocean? Okay, how the silicate rocks that have been chemically changed by water produce carbonate rocks in Earth's ocean. So let's just see what it says. So this is going to be based on the reading. So we're still from this. This is 9 through 13. Okay. Let's see what the questions say. Oh, it's probably this. Yeah, this is what it is. Chemical weathering of silicate rocks on Earth. So we need to make silicate rocks, see silicate rocks here, into carbonate rocks. So it says silicate bedrock plus H2CO3, the acid, dissolves into the river. I didn't mean to highlight everything there. Dissolves the ions into the river water, transports into the river, and then it says the silicate plus the calcium carbonate, shells of ocean plankton deposition in the ocean. Okay, so we're going to try to figure out which one is most like that. Water carries dissolved ion of the rocks to the ocean where they're used to form carbonate rock layers. Okay, maybe. Let's see the next one. Water combines with carbonic acid to weather the rocks, yes, which directly break down to form the rocks. No, we're not going from weathering directly to the rock, so that's not right. River water transports the rocks to the ocean where they form carbonate rocks. No, they have to break down first into the dissolved ions. It says that. Ocean water combines the rocks with calcium ion. No. That was easy. So there's no background knowledge needed from this. The answer to this was in the picture. So I would say this is like a 3 out of 10. Like, that was an easy question. You didn't have to know anything about silicate or carbonate rocks to get that. It's right here. Do you have to know how to read this and make sense of it? Sure, but you just saw me do it, and like, you just have to look at the steps here and it gives you the answer. Okay, let's see this part. Based on the model, which table correctly identifies the processes that form carbonate rock from silicates and the distribution of these materials? Okay, so automatically, this is a rock cycle question. So carbonate rocks and here, does it say? I just want to look at something. See, organisms making shells, things like that. Those are sedimentary. See, they create sedimentary rocks. So we want processes that create sedimentary rocks, okay? So we need sedimentary. So this is going to be a rock cycle question, okay? Process, ready? Crystallization. Wrong. That is not a sedimentary rock process. Crystallization, crystals, that's probably going to be more of like an igneous crystallization. Recrystallization is metamorphic though, but either way, crystallization is not going to be it. We're going to form a rock. Weathering does not form rock. Weathering breaks down rock. So these processes are wrong. I'm just looking at processes. Subsidence. Subsidence is when the land sinks down. And mineral precipitate is when it precipitates out of dissolved water. So I'm going to say carbon. It doesn't say anything about subsidence. But honestly, that might be in the picture. Let me just look. Anything about subsidence here? I don't see anything about subsidence. So I'm going to say that's wrong. Okay. Lithification, possible. That's like the creation of the rock. And then silicates get weathered. Remember, silicates go through chemical weathering. So this is possible. This is possible, number 3. Chemical weathering is not going to make carbonate rock. And then look, recrystallization, that's metamorphic. So I would say, based on that, 3 has to be right. Yeah. So we're going to go with 3 as the right answer just based on that. See how I eliminated through the processes? That's how I would do this. This question was pretty hard, though. I'm not going to lie. So I would say this is hard. Yikes. Like, I used a lot of background knowledge to do that elimination. So I'm going to say this is in like an 8.5. This might be like a 9 out of 10 hard. Like there's nothing inherently wrong with the question besides it's way too hard for this test. So I would say I'm gonna say this is a don't like due to how difficult it is. It should not be on the test. Too hard. So that's 4 don't likes so far, right? 4. We're up to 4. Okay. Scientists are developing solutions to reduce atmospheric CO2. Carbon mineralization is so we're reducing CO2. Carbon mineralization is a process that speeds up the formation of carbonate rocks. 3 of the 4 mineralization processes listed below take alkaline waste products, which is calcium ions, from the production of batteries and steel. So they take waste from batteries and steel and use those ions to combine with atmospheric CO2 to form carbonate material. Okay. So that's going to prevent the CO2 from going into the air if they use the process to make store it in a rock. A student made claims about the 4 carbon mineralization processes. First of all, what student is going to make claims about this? Like, the students are not going to be like, in my free time, let's make 4 carbon mineralization claims. Ugh. Which claim correctly evaluates a solution and describes how that solution reduces the impacts of human activities on a natural system? This is just like a word vomit, basically. So much here. Like, ugh. And we're only on question 13. It's just a blob of text and words everywhere. All right, let's start reading. Enhanced rock weathering stores alkaline waste products. So I'm literally going to try to find that right now. Okay. Look, enhanced rock weathering. Here it is. Alkaline waste products are spread on agricultural fields, coastlines, or added to seawater, where it then reacts with CO2 and stores it in solid carbonates. Enhanced rock weathering stores alkaline waste products. Okay, and increases the amount of ions being transported to the ocean. Okay, so if I'm looking at the picture, alkaline waste products plus CO2 makes this stuff, and then it's moved into the seawater, but it's on fields too. Increases the amount of ions being transported to the ocean. Okay, like maybe, I'm not eliminating that right now because maybe I like to do like hardcore eliminations, like definitely wrong, and I can't eliminate that yet. The below ground process, okay, where are we for that? Okay, here's below ground process over here. Remove CO2 in the Earth's atmosphere using metamorphic and mafic rocks to create carbonate concrete. So let's read. Atmospheric CO2 is injected into the ground, reacts with basaltic rocks. Basaltic rock is igneous, forming carbonate minerals that store into the ground. So it's not using metamorphic rocks. So that's why that's wrong. Again, that is rock cycle knowledge to know that basaltic rock is igneous. So that's automatically, just that fact, I would say is a 6 out of 10 difficulty. That's before everything else. Okay, so 2's out. Let's keep going. An above ground process combines alkaline waste products. So where's above ground? So that's right here, above ground process. Oh no, these all three are. An above ground process combines alkaline waste products and atmospheric CO2 to make carbonate rock powder, which decreases the amount of atmospheric CO2 that can be dissolved in seawater. So look, carbonate rock powder, concrete. I don't see carbonate rock powder here, but it does produce concrete and can be dissolved in seawater. But it says an above ground process combines waste products and CO2. Waste products and CO2. So waste products and CO2 into rock powder, which decrease. So that could be right. 3 could be right. We're not going to eliminate it yet. So now we have at least 2. Hopefully we can eliminate 4. Alkaline waste products combine with CO2 in reactors, creating concrete, which removes CO2 from the atmosphere. Okay, alkaline waste products combines with CO2 in a reactor and then creates concrete, which removes CO2 from the atmosphere. That is totally correct. So if this was me, I would pick 4, which is right, because that's just totally correct. 1 and 3, there's probably something wrong with it, but they're not as absolutely correct as 4. And we don't have time to sit here and dissect every single question because we're on a time limit, right? So if I'm a kid, this one sounds like it's the most right. So I'm going to pick 4 and I would get it right. But I would say this is a 7 out of 10. Again, this is a giant blob of text. And I would say I don't like it. I don't like it. I don't think it's a good question. I really don't. Like, what are we testing on this exactly? Like how it's a reading comprehension question. Like how well can you read this chart? There is no background knowledge here to get this right. There is the only background knowledge that I truly used was knowing that this one was wrong because it's not metamorphic. That is the only content knowledge. Everything else was just reading the picture, which just doesn't make for a good question in my opinion. So that's number 5 that I don't like. Okay. Base your answers to question 14 through 18 on the information below. Okay. Conditions of a polar vortex event. A polar vortex is a large area of low pressure and cold air surrounding the North Pole. When the polar vortex is especially strong, the polar jet stream stays farther north. So strong, the jet stream stays north. The polar jet stream is a fast-moving belt of westerly winds in the atmosphere. Okay, and it shows that here. There's our jet stream right there. We could see. Okay, and we have the polar vortex keeps the cold air contained over the Arctic. When the polar vortex weakens, it can cause the polar jet stream to change. Okay, so you could see that. Disrupted polar vortex does crazy stuff. Notable polar vortex occurred in January 2014. The model below represents conditions of the polar vortex that determine the extent of the polar jet stream affecting northern hemisphere during winter. Blah, 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 blah. That's what I got from that. Okay, let's keep going. Describe how the pattern of movement of the jet stream changed when the vortex changed from stable to disrupted. Okay, so look. Stable looks like a circle. Disrupted looks like 2 circles. So it's split. Change in the pattern. Okay. Now, change in polar jet stream pattern. So that's the disrupted polar vortex. So look at so I was looking at the wrong thing. Polar jet stream is this. So it's this, and now it's like this. So we could say it went from that to it's like more wavy, literally. Describe how one weather condition most likely changed for New York State residents. So polar jet stream. So here's New York. Yikes. So right off of that, like there it is again. Students had to know where New York was. That in itself on this would be very difficult for some people, which is sad. So you had to know where New York was on this map. So here's Florida, right? So New York's probably around there, right? So now you could see the polar front jet stream move south, so it's going to get cold. That's the answer. You could also say there could be more precipitation, but cold is the number one thing to get. So overall, I would say this is realistically, I would say this is like a 3 out of 10, but it's sad to say a lot of students don't know where New York is. So if you didn't know where New York is, that could make this very hard or not possible for you. But I thought that was fine. And you should know where it is. You should know where New York is. Okay. The weather maps below showed the maximum and minimum temperatures for January 6, 2014, when the U.S. was experiencing a polar vortex event. Okay. There's a bunch of numbers here. We got isotherms with temperature lines. Okay. So you could see the highest temperatures here. You got 13, 14, 36, 71. I'm just picking up random stuff. And then now you got minimum temperatures on Monday. Oh, maximum temperatures, minimum temperatures. So you could see they're dropping into the negatives, very cold, 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 cold. Which makes sense. Polar, right? Polar's cold. Explain how the maximum and minimum temperature maps on January 16th provide evidence for the claim that the central U.S. was most likely experiencing polar vortex. Central U.S. dropped into the negatives. The central U.S. is very cold. The central U.S. drops into the negatives. Very cold. That is very easy. 2 out of 10. Like, that's all you had to put. Like, the middle of the country is very cold. Nothing to it. That might be the easiest question so far. 15. The maps below show the weather information on January 4th and January 5th. The dashed line indicates the 32 Fahrenheit isotherm at 7 a.m. Okay. We should be knowing how to read these maps, by the way, from the state lab, the weather state lab. We looked at all these, so this should be fine. We got isobars, we got pressures, we got an L, that's low pressure, precipitation in that area. And then the H is high pressure, fair weather. They got fronts on the map, so on and so forth. This is a mid-latitude cyclone. Called that on one of my predictions. Which statement identifies the pattern of movement of the low pressure center? Pattern of movement of a low and weather condition indicated with the map from L from January 4th to 5th. This is literally doing what the state lab wanted you to do. So look at the L, the square. They boxed it for you. So we're here, and then we're to the right. So it moved east. It moved east. That's the answer. Like that actually might actually be the easiest question. This is a 1 out of 10. This is so far this is the easiest question on the test. Of course, if you don't know compass directions, that would be hard because you wouldn't know what direction. But look, there's a compass on the reference table, so you can get it. 17. The movement of the cold front associated with the low pressure system from January 4th to 15 is a result of what? So why does a cold front move? The movement of the cold front. Okay. The fronts are moving from the wind. The winds happen because of unequal heating of the Earth's surface. So it's 2. That question is super easy. So that is a basic weather question. I would say this is a 2 out of 10 question. I don't have to read the other choices. Very simple. 18. Based on evidence from see if all the questions were like this level, that's fair. But I mean, it's also very easy. But I'm looking for fives. Even if it's like fives with some twos and like a seven once in a while, 7 or an 8, like one of those, like that's okay. But like that's what we're looking for here. We don't need all this other garbage. Based on, and these are direct content questions. Like these are nice. They're good questions. It's testing if you can read weather maps and you understand basic weather, like which is what we're trying to teach in the course. Based on evidence from the maps, weather conditions in high pressure system are generally clear because high pressure systems are usually what? This is like a basic question on high pressure. High pressure are not near frontal boundaries or near areas of precipitation. That's true. High pressure systems are usually only located near cold fronts. No. High pressure is no storms. They're only near warm fronts. No. Located where isobars are closely spaced. Close spaced isolines would mean fast winds, so that's automatically wrong. So like that question is super easy. This is what I refer to as meatball questions. They're so easy. This is a great run here of the easiest questions on the test. 16, 17, and 18. Nice. Crushing those. Okay. We got the James Webb Space Telescope here. The James Webb Space Telescope orbits the sun in a complex path. I'm sure it does. This path allows it to maintain a fixed location beyond the Earth at an average distance of 1 point. So, look, first of all, a fixed location. Okay. At an average distance of 1.5 million kilometers from the Earth. The JWST specializes in the study of infrared radiation. Many objects, such as extrasolar planets, radiate large amounts of energy in the infrared range. Other objects, such as neutron stars, are hidden by dust. Visible light from these objects in the universe is stretched into the infrared range. Infrared radiation can easily pass through dust. Yes, we know this. So you should have learned that we use certain telescope wavelengths to be able to see different space objects, and specifically infrared for dust. On Earth, observing the infrared spectrum from celestial objects is difficult. Earth's atmosphere blocks some of the infrared spectrum from space, so this makes outer space one of the. That's why they put the telescope in space, so we don't have to worry about the sky. Okay. From the sun, the JWST average distance and velocity is approximately what? Okay. Oh, okay. So first of all, we're here. So you can see JWST is further away than Earth. See how it's further away from the sun than Earth? So we need to know. So this is kind of tricky because they want you to go here and figure out how far away Earth is. Look, mean distance from sun to Earth is 149.6. So A and B are out because the JWST has to be further away than 149.6. So now we're between 3 and 4. So just that right there, that's automatically makes this a 5 out of 10 because you had to know to go to the reference table to get that number. And then 1/5. So now with the same orbital velocity as Earth to maintain a fixed location, that is not true because if JWST is further away, it has to go travel in a longer path. So if you want it to stay lined up with the Earth, it actually has to move faster. It has to move faster to keep up with the Earth because Earth is on a shorter path. So that's intertwining with Kepler to get that right. So I would say that right there, to get that 50-50 adds at least another +3 difficulty. Like that's an 8 out of 10. That is a hard question, but I like it. I like that question. I do have to say, I think it's completely great. It's challenging, and we want some of those. But that's a fair, challenging question. That's high level, really nice. Whoever wrote that, a nice one. Okay, place a check mark in each row to identify whether each design criteria or constraint is a positive or negative trade-off of the development and use of the JWST. So, okay, so we'll just go down the list and see. Is it positive or negative trade-off? So good thing or bad thing? Ability to detect older, more distant object. That's nice, right? That's good. Access for repair. Well, that's not good because it's out in space. So that's a negative. High development cost. That's a negative. But the quality of the infrared images is good. So that's fine. So I don't know. That's fine. I'd say this is like a 4 out of 10 question. That's fine. Maybe I'll make it a 5 out of 10 because just let's say this. The 5 out of 10 question because if you get one wrong, it's over. So you had to get like you technically have to have 4 things right to get 1 question right. So I don't really like that. All right, which explanation uses evidence from the JWST to support the Big Bang Theory? The universe must still be expanding because the JWST observed that the visible light from distant galaxies had moved into the infrared range. Okay, so this is a redshift question. So redshift, we need to get longer wavelength. So this is saying the universe is still expanding because the JWST observed that the visible light has moved into infrared. That would be a longer wavelength. So number 1 actually is correct. You could see here, infrared is longer than visible. If you didn't know that, it's right here on the reference table. But this is hard, in my opinion. So we're just going to keep this one as maybe. The universe must still be expanding because the JWST observed the infrared radiation from distant neutron stars that formed the supernovas caused by the Big Bang. It said nothing about that. No. The universe must be stable and static. That's automatically wrong. Universe is expanding. Universe must be contracting. That's wrong too. Oh, see, the other 3 made that way easier. So I would say this is a 3 out of 10. Like, that's not that bad. That's like basic. Oh, more Big Bang. Basic. 3 out of 10. The JWST and Hubble Space Telescope allow scientists to observe stars at various stages of stellar evolution. Okay, again, we're going back to stars. There's so much stars in space on this question. It's crazy. I mean, on this test, it's crazy. So we're here in this area on the reference table. Okay, complete the table below using the names of all 3 stars in order of their ages. Okay, and then label their correct classification. Okay, we're going to get their ages first. So we literally have to plot these. Okay, we're just going to have to find these. So ready? 1 times 10 to the negative third and 8,400. 1 times 10 to the negative third right here. And then 8,400 Kelvin. So that's 6,700 to 8,000 right here. So we're here. So this is going to be, which one? That's A. Is a white dwarf. I could go like this. This is already complicated. 1 times 10 to the second, 9692. 1 times 10 to the second, 9,000. So it's a little before 10,000. So that's here. So that's a main sequence for B. I'm just doing A, B, and C just to make it easier. And then 1 times 10 to the 6, 3,500. Probably a giant. 1 times 10 to the 6 all the way up here. 3,500 is really cool. So, oh, it's a supergiant. They had to go to the HR diagram and find those 3 spots. Automatically makes it a 5 out of 10. So now we're going to put youngest to oldest. Ready? Main sequence first. So this should go 21 Lensis. We're doing the names of the stars. Number 2 is going to be the supergiant. Quyllur. And then the oldest one is the dwarf. WD 1202 232. Okay. That was not bad, but again, 5 out of 10 just for the reference table that's involved there. And then classification, I literally actually named them already. So that's done. So this one is a main sequence. You would write the whole word out. I'm just going quick. This is a supergiant. And this one's a white dwarf. So I'm going to keep it out of 5 out of 10. I think if you knew to use the chart, that this is actually probably like a 3 out of 10. But just in the time it's going to take you to do it, and you had to go to the chart and pinpoint the right spots and things like that, we'll keep it a 5. But I like the question is fair. It's a good question. The James Webb Space Telescope was used with the other telescopes to observe a very bright gamma ray burst. The release of gamma rays was evidence of 2 stars merging together. Spectral data allowed scientists to determine that the elements more massive than iron were formed. Okay. Elements more massive than iron may also form in stars at one point in their life cycle. So you need to remember iron and nucleosynthesis is going to stop the star from producing energy and probably go supernova or In this case, it did. Oh no, there were two stars merging together. So yeah. Okay. Which statement about the formation of these elements during the event is correctly supported by evidence from the telescopes? Okay. Elements heavier than iron are usually formed during the destruction of massive stars. That's yes. Supernova is generally how you get that. Elements heavier than iron are commonly fused together in main sequence. No, iron is like the star killer. Gamma rays are necessary for the formation of elements. No, we don't need gamma rays. Merging stars absorb the gamma rays, forming heavier elements heavier than iron. No. 23 is 1. This was easy. 3 out of 10. Basic nucleosynthesis star question right there. That's fine. Easy question. All right, let's move on. So base your answers to 24 through 27 on the information below. So it says the influence of volcanoes on Earth's systems. There is just so much volcano and plate tectonics and astronomy on this. It's unbelievable. Two of Earth's major volcanic eruptions occurred in 1883 at Krakatoa in Indonesia and 1991 at Mount Pinatubo in the Philippines. Both of these major eruptions produced large plumes, so I like this, of rock, ash, and gases that extended upward into Earth's stratosphere. Interesting. Now, there's not much mention of stratosphere except on the reference table. There is this. So we could see stratosphere here. So like that's dings in my head like that exists, right? Otherwise, they're talking like plate tectonics again. So really, we're here maybe. So we'll see. Global winds circulated the ash and gases. So now I'm also thinking, okay, global winds. All right, well, maybe like they can use this chart. Who knows? The model below shows some information about the setting of Southeast Asia. Okay. So there's our Philippine plate. So that tells me we are really on this chart. But again, we don't even know what the question is. So let's see. Based on the model, which tectonic interaction led to the formation and eruption of Mount Pinatubo? Okay. So here, so look, this is a plate tectonics question based on what's happening at these plate boundaries. So the first one says divergence between Philippine plate and the Pacific plate. So can we get it right off here? Philippine plate, Pacific plate. So not really. I mean, it's there, but it's better on here. So Pacific plate and Philippine plate. So between them is this pattern, which is there, but we didn't know what that was. That's converging. So based on that, that is not diverging. So that one's out. Transform movement at the Mariana Trench. So Mariana Trench is right here. Transform movement is right there, but doesn't look like that's there. So I would say that's not right. Convergence between Australian and Eurasian. So Australian versus Eurasian, they are converging. So that looks good. And then convergence between Eurasian and Philippine. Eurasian and Philippine are right there. So those two look like they're both good, but it's asking about Mount Pinatubo. So that's right here. So the Philippine and Eurasian plate are going to be closer. So 24, I like 4. I did not think that was hard. We'll say that's a 4 out of 10 just because you had to know how to read the chart, but not difficult. Number 25, sorry. Volcanic eruptions cause changes to several Earth systems. The model below shows the effects of large volcanic eruption like those that occurred at Krakatoa and Mount Pinatubo. What they have on the atmosphere, very small solid or liquid particles called aerosols. We should know what those are. Ejected from volcanoes become suspended. So for this, you should definitely, so it even says reduced radiation. If whenever there's a volcanic eruption or like an impact or something like that, the ash cloud is going to block the sun, making it colder in this area. And that's a short-term climate change factor. That could be, look, it even says 1 to 3 years. So that could be cooling for like about a couple years. Use information from the eruption model to describe how aerosols ejected from volcanoes affect energy flow into and out of Earth's system. Okay, let's just start with that because then it says also describe. Okay, so effective aerosols on energy flow. They lower energy flow. They block energy flow. So we could say aerosols block energy from entering. and leaving, really, because it's a double. It can't get out or come in. So that answers both of those. And then the change in climate, we set it. Cool down. So that was a very easy question. Again, I would say that's a 3 out of 10 difficulty. Not hard. Okay. Although volcanic activity can cause problems for humans, it can also provide benefits. The model below shows a 4-step process of converting geothermal energy into usable energy. So we're going to convert geothermal energy into usable energy, which includes mitigation of a cause of climate change. Okay, remember, mitigation is lowering the effect of. Okay. So based on the model, we'll look at the model in a second. With model of geothermal power plant with mitigation components, which row correctly identifies the step during which energy flows? So during which energy flows out of an Earth system. So let's start with that. We want to know which is going to be energy flowing out of the Earth system. Let's see. Capturing CO2 in thermal fluid. Is that energy flowing out of a system? I don't know. Remove captured geothermal fluid to produce electricity and hot water. So removing the captured fluid. Maybe. Injecting unused CO2 into the ground. Or 2 years later, CO2 reacting to form minerals within basalt. So that's like 2 years later. So we want to have energy flowing out of an Earth system. So flowing out will probably be, I would guess, removing the fluid, because you literally removed it. So that makes the most sense to me for step of energy flow out. But mitigation step, if we pick 2, it has to be 3. So is 3 a mitigation step? Injecting unused CO2 into the ground. Yeah, because you're mitigating the problem of CO2 in the atmosphere. So you're going to take it and then put it into the ground instead. So I like this one the best. I think this is a very hard question for someone, for a student to reason through. So I would say this is probably a solid 8.5 out of 10 difficulty. This is very hard. And I'm going to also say I don't like it because I think it's too hard for this test. So that is the 6th question that I say is not good. Like completely shouldn't be on the test. Okay. Remember, these are just my opinions, so feel free to disagree and tell me why you think it's a good question in the comments. I mean, it might be a good question, but for this test, you know, I teach mainly 8th grade, so for a 12 or 13-year-old kid to be doing this question, I think that's like they just had like I could see this being good for like an AP class, like AP environmental science, if they do AP earth science, like maybe that's good, but for this test, I don't think this is necessary. Okay, the Mount Merapi volcano hazard maps were made to identify areas of potential impact from pyroclastic flows as a result of previous eruptions, so areas of impact, potential impact. Locations in Zone 1 have lower probability of being impacted by a pyroclastic flow, which is hot ash and gas, while Zone 3 have the highest probability of being impacted. So you could see that's the darker area of the map. And that makes sense because it's closer to the volcano. And this is 2002, and there's 2011, and they look very similar, but some of them, like Zone 3 is more outwards down here. Well, whatever, we'll see what they say. Which statement correctly identify the probability of how these natural hazards have influenced human activities? Okay, let's check it out and try to eliminate. Forget the multiple choice. Let's just go down and try to get rid of these. Where I correctly identify the probability of how these have influenced human activity. Residents of Brongang downgraded their probability of experiencing pyroclastic flow after the 2011 map was created. So Brongang, that is wrong because now they're in worse situation. So 1 is automatically out, which means we just got rid of 2 choices. All right, we keep going. Residents in Brongang should install an early warning system sooner than the residents of Silo due to the predicted direction. So let's see Cello. Cello is basically out. So yes, this is a good idea for Brongang. An early warning system is needed in Monitelin because it's within 15 kilometers of Mount Merapi. So let's see. So 15 kilometers is here, and then Monletin, right? That is not within 15 kilometers. That should be in the circle if that was the case. So statement 3 is out, which means 3 is eliminated. So that leaves this number 2 is the only answer. So like for me, a strategy on this test, if you get to that point, like I would just move on just because you don't know what's coming up. Like maybe make a note, be like, okay, like I'll double check to read 4 and 5 to make sure they're good. But like a time saving technique is like if you conclude an answer based on eliminating all the other ones, I would just pick it and move on and like come back to it if you have time at the end, because we don't know what the rest of the test is going to look like. It could be like we could need a lot of time for some of these questions. So I would just gamble on that being right, in which case it was. Okay. Okay, 28 through 31, New York's concrete industry. The production of concrete starts by mixing limestone and clay together, which are heated and dried in a kiln to produce clinker. That's a fun word. Clinker is then pulverized into a fine powder and mixed with gypsum to make cement. Aggregates, such as crushed stone and sand, are added to the Portland cement along with water. Let's just highlight aggregates being with our examples there. Along with water to make a new product called concrete. So, okay, great. Mineral resources in New York State. So automatically, I'm like, boom, we're going to New York State map. Look, energy and mineral resources of New York State. Have allowed the construction facilities that produce cement. Which resource is correctly matched with the location where the resource is found? Okay. Clay and Manhattan prong. So we're just going to use this. This is easy. Well, allegedly. Clay, Cl. Is Cl in the Manhattan prong, which is in this area here, which is north of Long Island. So is there clay over here? There's clay right there. So I would say no. And this is just me going pretty quick. So we'll see if we could just get one absolutely right. Limestone in the Adirondack Mountains. I already know that's probably wrong because mountains generally don't have limestone. So mountains here. And then limestone. How would we see that? Is there anything on this? Yep. So in here, is there limestone with the squiggly lines? So this is gneisses, quartzite, marbles, metamorphic rock, and then the sprinkle sort of pattern is anthracitic rock, which is also metamorphic. So that's out. Carbonate rock from the Hudson River Valley. Let's see. Carbonate rock from the Hudson River Valley. Is carbonate rock on here? Yes, it is. Carbonate rock, and then Hudson River Valley is going to be right here. So we're looking in this area for that shaded area. So that is possible. I see it right here. So maybe we like that one. Gypsum from the St. Lawrence Valley province. Let's see. Gypsum is G. St. Lawrence Valley province is up here. So we're looking for gypsum up there. It's not there. So gypsum's only here. So that gets rid of 4, which means 28 has to be 3. And that question is really easy. 3 out of 10. Easy. Pie charts below show some information about the carbon footprint of the 3 stages of concrete production. Carbon footprint is the percent of carbon emissions generated at each stage. Carbon footprint at each stage of concrete production. Okay, so we got clinker, electricity, transportation, and this is the carbon footprint at each stage. So 100% carbon footprint, which is the amount of emissions. So the most at the clinker stage, it's 100%. Then 94% clinker emissions and 6% from electricity. And then over here, when we're making concrete, it's clinker, electricity, and transportation. But it's mostly clinker, it seems like, by a lot. Let's see. Which statement identifies the relationship between 2 Earth systems that are affected by the production of concrete? Okay, ready? One by one. Elimination. During the concrete stage, 11% of emissions are released from the geosphere. Look, concrete's We're looking for 11% from the geosphere. 11% would be 6 plus 5. So is electricity and transportation releasing from the geosphere? I don't think so. Into the hydrosphere from transportation. So it's saying 11% from transportation. No, that's only 5%. So I'm going to put that as a no. During the cement stage, we're going to see how we do. Like, I like to, if I eliminate all of them, then I did something wrong. My thought process is wrong, but we're going to see how it goes. During the cement stage, 100% of emissions are released from the geosphere into the atmosphere from clinker. Cement stage. Where's the cement stage? No, only 94% is clinker. Okay. During the concrete stage, 5% is released from the atmosphere into the geosphere from transportation in concrete stage. Concrete, boom, 5%. Yeah. During the cement stage, 94% of emissions are released. We already know. Cement stage, 94% is released from clinker. So that's also right. Okay. Now so we have 2 right, but look, this is perfect. Is the transportation's like a truck, right? So they're saying it's going to be emissions are released from the atmosphere into the rock. That's not how that works. So it has to be 4. Because the emissions go into the atmosphere. The emissions are the smoke and stuff like that, the pollution. Honestly, this was pretty easy, but we'll say it's a 4 out of 10. I don't have a problem with that question at all. Okay, concrete has been used for centuries in the development of urban areas. The model below shows some information about urbanization. I'm just going to pause and say, by the way, if you're thinking that these questions are like 9 out of 10, 10 out of 10, I'm going to argue and say that there's a content issue that you're having, meaning you're not very familiar with the material per se, or you're not seeing something in the diagrams, or you're not reading correctly. I don't think at any point with these 3 or 4 out of 10 questions that you should be saying that this is a 10 out of 10. Like, I could see if you say this, you think this is a 5 out of 10, but this was literally just reading the sentence, matching, and then knowing that emissions go into the atmosphere, not into rock. So that's like very basic content to know that smoke goes into the air, not into rock, to be able to get that 50-50 done. Yeah, just something to think about. Okay. Concrete has been used for centuries in the development of urban areas. The model below shows information about urbanization. Okay, urbanization just meaning we're building more buildings. Urban, you're building city-like structures in the building. So you could see more trees and stuff like that, and then you got your cities. Okay. Circle 2 of the 3 systems below that are influenced by the use of concrete in the development of urban areas. Okay, so we have to circle 2 different ones. Okay, development of concrete. And then describe an impact that building cities has on the water cycle. All right, so I think we could say, look at this and try to get, there you go. Evapotranspiration went down, building the city. And then we could say, look, there's 10% runoff here because all the plants are absorbing. And now there's 55% runoff. So that's an easy one to talk about. And then we can also, so there's more runoff. And then there's more infiltration here and less infiltration here because they paved. So that's a lot of talking points for the impact. So now I could say which one's going to be impacted by that. So I could say the atmosphere. And I could be like atmosphere receives less water vapor. Because there's less evapotranspiration. These are water cycle processes. And then I like maybe I already picked atmosphere, so I got to be able to defend hydrosphere or geosphere. Geosphere, I'm going to pick geosphere and say less water is able to get in. Or is that? Yeah, I'll just say, actually, I like this one. Let's go hydrosphere and say there's more runoff. right? I could also say geosphere, less water is going to infiltrate into the ground. That's fine too. But all right, I mean, it's a two-part question. A little challenging. This is pretty content related. You got to know the water cycle. Plus, you're going to have to interpret the chart. Plus, you got to know what urbanization is. It's kind of hard. Let's say this is like a 6.5 out of 10. I don't see any issue with the question, though, honestly. Like, this is kind of weird that you had to circle one and then circle one, like the way they worded that, but it's not horrible. I mean, it's not the worst thing. Okay. Engineers have developed a newer type of concrete called porous concrete. Okay, we should know porous means it's got holes in it to address some environmental issues that accompany urbanization, so it's going to be able to absorb water better. An investigation was completed by an engineer in northern New York using the properties of water to determine water's impact on the concrete. The tables below show some information on the properties of concrete and water, and the photographs show the result of the investigation. So you could see new insulation, and now there's more cracks in the rock. What does it say here? Traditional only has 3 to 5%, porous has 15 to 22. So there's more open space. And then this is just saying properties of water. So we could say the temperature of liquid water, density of 1. Okay, great. Let's see what the question is. The 6 factual statements below describe some considerations for the use of porous concrete. Which 2 statements identify constraints that we want to support the choice of traditional concrete? So we're saying traditional concrete's better. We want it to say traditional is better. And we're going to think about that as we go. We're going to try to eliminate. Okay. Sand cannot be used on new porous concrete for ice control. That's a big problem. So I would say that could be good. Porous concrete typically has cooler temperatures during the summer. That's really good for porous concrete. So that's not going to help that's not what we want. We want we want to say traditional is better. Porous concrete has a higher cost. So that would mean traditional is better. So we like that one too. Okay. Porous concrete cannot be used for roads, bridges, dams, and building. That's a big problem. So that means traditional is better as well. Hope I'm thinking about this right, because now I have 3 right things and they're only saying 2. Porous concrete filters sediment from runoff. That's good for porous concrete, so we don't want to talk about that. Porous concrete has rougher surface and provides better traction, so that's also a positive. So we got 1, 3, and 4 that are good. So 5's out, 2's out, 3 and 6 are out. Oh no, 6 is out. So that means it has to be 4. Just based on those choices. I really didn't think that was that bad. Well, but it was a lot of reading, and this is kind of backwards thinking here, so let's just call it a 5 out of 10. Fine. I don't see a problem with the question, though. Okay. All right. Base your answers to 32 through 36 on the information below. Lake Nyos sits on the crater of an inactive volcano, so it's not active, within the Oku volcanic field. Lake Nyos has almost no convection. Okay. A layer of warm water always sits on top of a deep layer of cold water. Okay. In 1986, a large bubble of carbon dioxide that was trapped at the bottom of the lake rose to the surface. The carbon dioxide then moved down into the valley, killing tons of people and a lot of farm animals. That's livestock. The map below shows the locations and names of the features that include Lake Nyos. The inset map shows the location of the volcanic chain in Africa. Oh, that's terrible. Okay, the infographic below shows some information. So you got the CO2, the rising, and the volcano there. And then it went down the valley over here. Went in here and killed everyone. CO2 flowed down the sides of the volcano into the valleys. Okay, let's just see what we need to read. Which factor most likely caused the movement of carbon dioxide gas from the lake downhill into the valley? So we need to move the CO2 down. So how are we going to get CO2 to move down? The air temperature on top of this is a weather question, actually. It's a pressure question. Temperature and pressure question. Okay, air temperature on top of the mountain increased. That automatically doesn't really make sense to me. Because if you're going on top of the mountains, it's cold. Causing the CO2 gas to sink and flow into the valley? No, that's not going to make CO2 sink. Okay, pressure decreased as CO2 gas flowed down the side of the mountain. Remember, if pressure is going down, that means everything is going to go up. Low pressure rises, so I would say that's wrong. The density increased over the lake because CO2 gas was more dense than the surrounding air, causing it to flow down. If it was more dense, it would flow down, so that could be it. Relative humidity was higher at the surface of the lake than the valley, causing the relative humidity is going to have no reason why the gas would sink. So sinking, I would say the only answer has to be 3, that it's more dense. So this was just a basic density question. So this is pretty easy. I'm going to say this is a 3 out of 10. Not bad at all. Do I want a 3 out of 10? Maybe I'll say it's a 4 out of 10. But I still don't think it's that bad. Okay. Using evidence from the infographic, which statement describes the best human response? Notice as I'm highlighting what the question is. I need the best human response that would reduce the loss of life due to a future release of the trapped gas. So they're basically saying, if this were to happen again, how do we prevent humans and cows and stuff from dying in there? Relocate the homes to higher ground. Yeah, that would probably be good because look, the CO2 stays down here and there's nothing up here. So if we move the houses up there, they're out of it. So that could be it. Plant more trees. There's already trees down here and that didn't help. So I would say that's not going to be a thing. Drain the lake to remove the source of CO2. The source of CO2 is not the lake. It's in the volcano, so that's wrong. Relocate homes to a different part of the valley floor. No, the valley floor is completely covered. So 33, the only possible answer is 1, and I didn't think that was that bad. I would say that's easier than 32, so that's a 3 out of 10. Okay. The magma creating the Cameroon volcanic change is rich in CO2. 2 sources of CO2 in the magma are found in surface and mantle minerals and rocks. Okay. Carbonate minerals and rocks, which contain carbon and oxygen, are located on Earth, are broken down and melted. Okay. So we melt the rock, and then it releases the CO2. Complete the qualitative model below by writing the letter for each choice in the correct space in the model to represent one pathway for the movement of carbon that was responsible for the increased levels of CO2. Okay. So we just want like an order of how it happened, basically. So let's start. It's saying carbonate minerals and rocks. Okay, that's it. So we need to melt the rocks. Heat is applied to the rocks. So I would say, I don't know if this is right yet, but I like this first. Carbon dioxide leaks from the rising magma. Carbon dioxide is released from the rocks and minerals, or carbon dioxide dissolves into the magma. Okay, so I like B next. We're going to apply our heat. Then we're going to release the CO2. Then we're going to dissolve the CO2 into the magma. And then we're going to leak the CO2 into the lake. I think that makes sense. I think that was pretty easy, honestly. But I could see why someone might think that was kind of hard. But I'll give it a 5. But I really want to give that a 3. But I'm thinking in my head, I'm like, okay, like we're already on question 34. People are getting tired by this point. So I don't think that's bad, though. It makes sense. It's like a logic question. Okay. Describe how the minerals within the rock of the continental segment are different than those found in the oceanic segment. So we want minerals in continental versus oceanic. So right when I think continental oceanic, we're going to think plate tectonics. And I like to think of the difference between continental and oceanic crust. So this was in the plate tectonics unit. So continental crust is less dense, made of granite. And then oceanic crust is more dense, made of basalt. Okay. Now, how is the minerals within the rocks different between them? Use at least one specific mineral to support your description. So we need to know what minerals are in basalt and what minerals are in granite. Now, here's my problem with this. If you have a student who didn't know that oceanic crust is basalt and continental is granite, you're never getting this question right. So that's the first part. So that's the content. So I would say that's a 5 out of 10 automatically. But then we have to know what minerals are in them. The only way to do that is on the reference table. So we have to go to, they're both igneous rocks. So we're here. Right? Am I right? Yeah. Look, granite and basalt. The minerals in there are here. So like granite has a lot of quartz and basalt doesn't have any quartz. So because the quartz is only in the granite. So I would say that's like the first mineral I see. So we could be like, describe how the minerals within the rocks are different than those found. So I could be like, I could say continental crust has more quartz. Like that's all you have to write. But then then the kid has to go to the reference table and then find those minerals and then make that distinction. I'm gonna say that adds like 3. This is like an 8 out of 10 question. This is hard. I'm gonna have to say I do know that people like in the community had an issue with this question. I'm gonna say hot take. I don't have an issue with this question. It is hard. But I do think that like basic knowledge of oceanic and continental crust, like why, like that they're made out of basalt and granite, is like I don't know, like should be taught. But I guess if you didn't know to teach that, then this could be. Then you didn't, your kids wouldn't know. If you didn't teach that, then there's no way your kids would know that. So, yeah, that's all I have to say about that question. It's hard. We'll just leave it at it's hard. And that's that. Okay. After several studies in the 1980s and early 1990s, scientists and engineers proposed installing degassing pipes in Lake Nyos to prevent further loss of life. So I guess like they're saying, so these pipes like get the carbon dioxide out of the water to prevent the bubble from happening. These pipes function in 2 stages. In stage 1, CO2 would be removed by using a powered pump to pull small amounts of cold water from the bottom of the lake to the surface. Okay. In stage 2, the bubbling from the CO2 coming out of the water creates suction and makes the process self-sustaining. The first degassing pipe was installed in 2001, with additional pipes installed in 2011. Carbon dioxide now comes to the surface under its own pressure with no pump required. So they basically like automated it. It's like a suction sort of thing. So it's constantly just happening on its own. Okay, but it needs a pump. Oh, no pump required anymore. Okay, so they needed the pump to initially get it going, and now it's just automatic. Okay. That makes sense. Which description best explains why self-sustaining degassing pipes are the best solution for reducing the risk of future outgassing events? Okay, let's see. Self-sustaining degassing pipes leave the cold water at the bottom of the lake undisturbed. This allows the natural processes to continue without disrupting the natural system. I don't know why that would make it the best solution, but I can't really eliminate it yet because let's see the other ones. The self-sustaining pipes allow the residents of the rural Cameroon to be less dependent on scarce fossil fuels or electricity needed to operate the pipes. Sure, they don't need any energy to run the pipes, so that could be possible. I like that answer better than 1 so far. The self-sustaining degassing pipes reduce the risk of future volcanic eruptions by removing the carbon dioxide from the magma. Okay, there's no future volcanic eruptions because it said initially here it's an inactive volcano. So there is no future eruptions. So that one's automatically, that's a definite elimination. The self-sustaining pipes allow the warm and cold layers of water to mix. I don't see any mixing happening. So I think for 36, the best answer is 2. It's just like a reading question. It's fine. 5 out of 10. It's fine. Okay. 37 through 41. Complex tectonics. There's so much plate tectonics on this. Mariana Plate is a microplate that's located west of the trench. Mariana Trench. Geologic activity caused a section of the Philippine Plate to break off. We should already know that we're on this chart right here. And become the Mariana Plate. This microplate surrounded by many features and complex plate boundaries. V through Z represent locations on Earth's surface. Okay. So these V, W, X, Y, and Z are just different locations. Okay. Which statement correctly describes the pattern of ages in the rocks found in the model? Okay. All right. We're going to the elimination game. Here we go. Location Y is younger than V. Let's see. Is location Y younger than V? I don't know yet. Because Y is closer to a convergent boundary? Maybe? It's kind of weird to compare those two on such far away locations. But maybe. Let's go on. Location W is older than X. So W's located. No. So this is back. We already tested on this. The further away from a ridge, the older it is. So X is older than W. So that's just wrong. Don't like that they're testing on the same concept with the ages. They already did this. Location Y is older than Z. Let's see. Is Y older than Z? Yes, definitely. Because this is going to go this way. So Y was there first. This is the best example we have so far. Because it's closer to the convergent plate boundary. I like that a lot. Location V is younger than W. No way. Because this is the ridge, so V is older. So I'm going to go 37 is 3. Final answer. Lock it in. That makes sense to me. I would say this is a 4 out of 10. But if you got the relative age question wrong earlier in the test, you're probably getting it wrong twice because you don't know how relative age works from a ridge or near a subduction zone. So that's a double jeopardy, which means that should not have been on this test. So you got to pick one. You can't double test the same topic. Not fair for the kids. Okay. Plate interactions cause plates to move also form features on Earth's surface. Which table accurately identifies the process associated with the features found in the model? Okay, constructive, destructive. Constructive means you're creating, and destructive means you're destroying. So first of all, let's just go and see. Divergent plate boundaries always construct because the lava comes up from the middle. So we want divergent to be constructive. So that's right and that's right. So that means this is out and this is out. So now we're left with 1 and 3. Do volcanoes construct or destruct? Arguably, they could construct new rock and they harden, or they could destroy because they're lava. So we don't know. And then a trench is a subduction zone. When you go down a trench, the rock melts and gets destroyed. So that has to be destructive. So the answer to 38 has to be 1. So again, process of elimination for that one, I would say this is a 5 out of 10. This is right down the middle of the road. Easy. I mean, it's basic content question. In my opinion, I say this is a good question. I like it. All right, 39. What are we up to? 6 that I didn't like so far. 6 questions. 6 questions, like 2 or 3 very hard ones that are just hard. And then the rest is like middle of the road or easy so far. This is my opinions, remember. 4 tectonic processes listed below describe one stage in the cycling of Earth material in the Mariana region. Write the letter of each process in the correct sequence to describe the cycling material from Y to X. Where's Y to X? Y. Okay, so Y, so we're going subduction to volcanic eruption? Or, I don't know, Y to X? Yeah, we are. That's what we're doing. Okay, so we need to subduct first. So we're going to subduct the Pacific plate. Then it's going to start to melt. So then this is next. Then the magma rises up and then it erupts. Bada boom, bada bing. That was really easy. But again, You need knowledge of plate tectonics and how subduction zones work. But I feel like what they are asking for here is very basic. So I would say we're going to call this 5 out of 10 again. It's middle of the road, medium, but solid. Okie dokie, we're going on. The model below shows some information about the rock formation in the area surrounding the Mariana microplate. See, I'm just going to also say something like, this test is way too focused on astronomy and plate tectonics. Where's the rest of the year? Like, we could have taught everything on this test in 3 months. The other 7 months wasn't even on this test. Like, that I have an issue with, because if you have a kid that's weak in these two topics, they're going to fail. It's 100%. They keep asking questions from the same topics. I don't understand that. Okay, let's see. This is blah, blah, blah. It's a subduction zone. It's literally a subduction zone again. Look, subduct, melt, rise, volcanic eruptions. Okay, let's see. Based on the model, which row identifies the correct combination of formation, rock forming process, and rock name? Oh my gosh, it's a rock cycle question again. Okay. So for this, we need to know that this is all igneous, basically. There's a little metamorphism in there. And how do I know that? Because I'm looking at the patterns of these rocks. And then you would have to go, if you didn't know that, where's this one? See the patterns on here? These will correspond to the patterns that they put here. The dots is over here, so that's sandstone. I don't know if we're going to need that, but that's where those patterns come from. Okay. Is A an eruption? Could be. It's on the volcano. Does eruptions make granite? No. Granite is made deep inside the earth down here. So this is a rock cycle question. Okay. Solidification at B? Maybe. There could be solidification in a magma chamber. And does that make peridotite? Look, peridotite in a magma chamber, that is possible. So I like this one so far. Is C conglomerate? C is this line thingy. The line thingy's over here. Conglomerate's down here, so no. And then D, heat and pressure for schist. D is these lines here. Heat and pressure could be possible, but what is this? That pattern is schist. It is. That should be happening pretty deep in the earth, which it is. So now I'm between 2 and 4. So I'm going to probably eliminate B because it's in the magma chamber. So I'm going to say that's probably not solidifying, which means I have to pick 4. So again, rock cycle question, but that was kind of harder than normal. That required a lot of background knowledge from me and reasoning. I'm going to say that's a 7 out of 10. That's pretty hard. So again, I don't know how many hard questions like this we've seen so far, at least 3 or 4. I would say 1 or 2 really hard questions should be on this. Like, there's too many really hard questions. But like a couple is okay, but they're put way too many hard questions on this. Okay. At the trench, water-bearing minerals are brought into the mantle, altering the melting point temperature. The graph below shows some information about the melting of basalt. Pressures on the graph are in kilobars. Okay. Name one feature, tectonic feature, that forms in an area above melting crust. It's a volcano. That's easy. That part's easy. But again, it's 2 questions in 1, of course. Then use evidence from the graph to describe how the presence of water affects the melting point. So let's see. Look, temperature of melting point for dry is like 1500. And then the temperature, if you wet basalt, is going to be lower. So we'll just say water lowers the melting point. That's it. So I would say that's like middle of the road, 5 out of 10. Not that bad. Okay. Planetary transits. The transit of a planet across the disk of the sun may be thought of as a special kind of eclipse. So they're just saying Venus is going across the sun. Boom, 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 boom. And then Mercury went across here. Pretty cool pictures, actually. Those are real. Time-lapse photograph shows 2 planetary transits. That's pretty cool. The data shows some information about the transits of Mercury and Venus. Which piece of evidence explains why Mercury and Venus are the only planets in our solar system that transits? Because, okay, when viewed from Earth, it's because they're closer to the sun than the Earth. Like, if the sun's here, you got Mercury, Venus, and then Earth, and then the rest are out here. So we're obviously only going to see Mercury and Venus cross the sun, because if we're looking at the other planets, we're looking away from the sun. So that's why. So we could say it's not because they're smaller. It's not because they have a different tilt. They're the only planets between the Earth and the sun. Yeah, 3. That question was really easy. I'm going to say that's like a 2. But again, so much astronomy. They only put astronomy and plate tectonics on this test and 1 question on like the carbon cycle and then 2 questions on like environmental science. I don't know what they were thinking on this one. It's not fair. It's like too targeted. You're going to get, like I said, the kids who are weak in astronomy and plate tectonics, you're going to get all these wrong. It's a guaranteed fail. Which evidence-based statement explains why Mercury has more transits of the sun than Venus for the same time period? Mercury orbits the sun approximately 2.6 times faster? Okay, so this we need the reference tables. So we need to know the revolution of Mercury and Venus. Period of revolution. Mercury's 88 days versus Venus 224. So is Mercury 2.6 times faster? You would just do 224 divided by 88. Let's get our calculator. Wow, a calculator question. 224 divided by 88. That's 2.54 times. So approximately 2.6. Mercury orbits 2.6 times faster, resulting in great. So that's right. Venus orbits 2.6 times faster? No, it takes longer. Mercury orbits the sun 2.6 times faster than Earth. I don't think so. Earth is 365. So if you're doing 365 divided by 88, you're not getting 2.6. Venus orbits 2.6 times faster than Earth. Nothing to do with that. 43 is 1. That was really, really easy. 3 out of 10. The Kepler Space Telescope used planetary transits to find planets outside our solar system. Kepler 16b was the first planet discovered in a binary star system. Binary star systems contain 2 stars. In this solar system, the stars Kepler 16a and Kepler 16b orbit each other. Okay. Describe 2 characteristics of the Kepler 16 stars compared to our sun. We're going back to the HR diagram again. Like, you're testing, we already did this. Like, I don't know why they keep retesting. You're going to make kids that don't know that one chart get so many questions wrong, and it's like an auto fail. Not fair. Describe the kids that did the best on this test were the best in astronomy and plate tectonics. That's it. So if you were one of the students who got above like an 85 on this test, because like there was 4 or 5 questions right off the cusp that I said were ridiculously hard. So like let's say you got all 4 of those wrong, and then you got 3 more questions wrong that are just kind of hard. You were rushing or you didn't see something. Like you're already at not doing great. Well, you're already like at 8 or 9 questions wrong at that point. And then you have to get all the other ones right. And then if you're a kid who didn't know these topics, you'll probably get half of all these wrong. So it's I don't know. I don't know what they were doing here, honestly. Describe 2 characteristics of the stars compared to the sun. So let's look at this. So we only have temperature and luminosity. Wait, describe the 2 characteristics of the Kepler 16 stars compared to our sun. So let's look. Our sun is here. So we have a little more than 1 luminosity. It should be basically 1. And then the temperature is like 5,700. Luminosity is 1, temp is 5,700. So characteristics, these are lower luminosity and colder. There's your 2. Again, I don't know. This is 3 questions in one. Lifetime, if they're here 4,500 with a 0.14 luminosity, 0.1, 3,500, they're a smaller main sequence. These are smaller stars. So the lifetime is going to be longer. But I don't think that was hard. But again, if you're weak in astronomy, you're getting double, triple hit with the same content over and over and over. So HR diagram, I don't think it was that hard. 4 out of 10. Based on the character, we already did fusion. We're doing fusion again. Based on the characteristics of Kepler 16a, which row best describes the fusion occurring within the star and correctly identifies a star that has similar characteristics? Okay, 16a is here, so now we're on the HR diagram again. 4,500.14. 0.14, 4,500, 3,4 right here. We're like somewhere over here, so we're basically main sequence. So we're going hydrogen to helium. So fusion of hydrogen into helium, great. And are we similar to Saigani B? Look, Saigani B is right there. I guess so. So hydrogen to helium similar to Gliese 725b. Where's that one? That's here. So this one's closer to 0.1. So I'm going to say the answer to 45 is 2. But again, that was a 4 to 5. We'll say 5 out of 10 because now we're getting later in the test. We're tired. We've already done this, the HR diagram. You're double and triple hitting kids. Not fair. Graph below shows some information about the dimming of the stars as they transit them. So from here, we're normal, and then all of a sudden you're lower in luminosity, and then here you're normal again. So the transiting happened there. And then here, this is kind of different. But then here it's very dramatic. So like basically from, my line is really bad. Like from here to like here, that's when that one was blocked. Calculate how long it took the 16b to transit both stars. So let's just start for that one. So transit time here, this is 1 o'clock, 2 o'clock, 3 o'clock, 4, 5, 6, 7, 8. So we'll say it's from 1 to 8-ish. So that's about 7 hours. And then here we have 1, 2, 3, 4. So this is like from, let's just call it 1:30 to 3:10. That's like an hour and a half-ish. So like, I think that is kind of weird. So we'll just call that like just to figure that part out, I'm thinking as a kid, that's like a 6 out of 10 difficulty. And then explain one reason why the planet transit takes a longer period of time to cross a star compared to the Kepler star 16b. That's Kepler again. Kepler's laws. We already did Kepler's laws. They keep asking the same questions in different ways, testing the same content in so many multiple different ways. Not great. Now we know why the passing rate was so abysmal, because they kept hitting the same topics over and over again, and if you're unfamiliar with it once, you're not getting it later. That's probably why there's such a disparity of some kids doing so much better than other kids, because if you were strong in those 2 topics, you're going to do way better. If something's taking a longer period of time, it's further away. That's Kepler's third law. Whoopsie. Ignore that random line. Yeah. Okay. 47 through 50, the last cluster, the Siberian Traps, are one of the largest igneous. We're back to rocks. Let me guess. Are we doing plate tectonics occurred 252 million years ago? Ooh, do we have to use the geologic timescale for that? 252 million years ago. Look, that's between the Permian and Triassic. It's estimated that 4 million cubic kilometers of magma erupted to form the 3-kilometer thick structure, the craton. Oh, a craton. Craton is the center of a continent. It's ancient continental crust that's really, really old and untouched. So we got a lot of ancient, really old rock there. Includes the Anabar Shield, which is the oldest original bedrock in the region. And we have a map. All right, let's just look at the questions here. Develop the model in the space provided that indicates how the Siberian traps were formed. Okay. Your model must include 2 arrows to represent the movement of magma within a plume. They basically gave you the answer. Look, rising magma spread horizontally below the boundary. It's a basic convection pattern. So we should do this. Whoop. Whoop. That's it. Easy peasy. We'll say 4 out of 10. Which statement correctly describes the physical and chemical properties of the basalt in the Siberian traps? Yikes. We're doing this again. We're going back to the igneous rock chart and we're looking at basalt. Look, basalt. It's got a lot of plagioclase feldspar, pyroxene, and olivine, and a little amphibole. Basalt has large crystals? No, because igneous rocks, the longer they cool, the bigger the crystals. So that content you needed to know. So that automatically makes it a 5 out of 10. And then we use the chart, right? So that adds another 2. This is at least a 7 out of 10. Plus, we're tired, test fatigue. We're beaten down by this point. We're at another one. This is like an 8 out of 10 question at this point. Okay, so these are out, but small crystals. High amounts of iron and magnesium, or does it have high amounts of potassium and sodium? So look here. Look, iron and magnesium here. Increased potassium, sodium to the left. Basalt's on the right, so it's increased iron and magnesium. So this is 3. 8 out of 10. Hard. And at this point in the test, like that's a lot. But the content that wasn't on the reference table that you had to know is that igneous rocks, basalt cools fast because it's towards the surface of the earth. And that's going to be small mineral crystals. Hard. Norilsk, Russia is a mining town on the western edge of the traps. We have large deposits of nickel-bearing ore. So now I'm thinking of the resources page. Processing the ore releases sulfur dioxide. Okay. Sulfur dioxide causes breathing issues from the creation of aerosols. Again, aerosols, smoke in the air. We're going to block sunlight, get cold. So we did this. We just did a question on aerosols. Why are we doing more aerosols? Look, aerosols cool. So atmosphere warmer? No. But again, like it's a double jeopardy. If the kid didn't know before, they're getting it wrong again. Atmosphere cooler temperatures. Yep. So, and then they didn't even put atmosphere in the other one. Let's just see. We're releasing sulfur dioxide. That could be an acid rain. Look, sulfur dioxide emissions. All right. So one's out. So let's see this one. A decrease in acid rain. No. Sulfur dioxide is a pollutant, so you get more acidity. Decreased plant extinction. No, the acid rain is going to kill them plants. Increased plant growth because more acid rain. No. So it's 2. I don't know. I'm going to say this is like a 6.5 out of 10. I'm going to actually say this is a 7 out of 10. It's just so content heavy. And then the kids need to know that sulfur dioxide would cause acid rain. Did it say that anywhere? No. So they would know, okay, sulfur dioxide is a pollutant. So then that's going to make the rainwater more acidic. Yeah, it's hard. The nickel deposits in Norilsk are found in the same mine with large deposits of copper, cobalt, and platinum. Nickel is rarely found as a resource in New York State. Which row identifies the mineral deposits that are found with the nickel deposits in New York State and the processes that most likely form these deposits in New York? And so we need to find which row identifies deposits that are found within the nickel deposits in New York. Okay, so we need to go to the chart here. and look for nickel deposits in New York. So let's look for nickel. NI. So go to NI right here. So we're here. So look, Fe and rare earth elements. So iron. Iron and rare earth elements right there. I don't even have to do anything else. That actually was really easy. I would say so, but you had to look at the reference table. So, and it's kind of like a word vomit here. So I want to say this is a 2, but we're at the end of the test and we're running out of time and all this stuff. So we'll bump it up 2. So we'll say it's a 4. But I didn't think that was open. All right. Well, if you didn't see here, the conversion chart. So like you needed a 21 to pass. So if you think about that, right? 21 out of 50, that's a 42, right? So you actually needed 42% to pass for a 65. So that's the curve. And, you know, you could see actually right now, if you got like a 58 on this test, like you only got 16 questions right, you know, which would be, you know, and do the math, you got a 16 out of 50 if you got a 58, which means you actually got a 32. So I would say there's probably like 10 hard questions on this one. Let's just say you got all the 10 hard questions wrong. And then there was 2 that were like, one that was like impossible. That number 4 question was literally impossible. So that's just say that's automatically wrong unless you got lucky. So if you got all those wrongs, you're already at an 88, and then you had to get all of the other ones perfect, which is very unlikely. So I would say like that's why a lot of kids, at least a lot of my students, were in the like, you saw a lot of low 80s. But if you had low content knowledge in astronomy or plate tectonics, you know, you're getting another 10, 15 questions wrong right there. Like, and so then drop to, you know, now you're in the low 70s. So I would guess for the majority of New York State, that's like where a lot of people ended up because the test was so focused on the same topics over and over again. So it's just they kept getting the same questions wrong over and over again, and that's just going to lead to very low scores. So I like to say at the end, my overall score of the test, I would say this test was way too hard and there were errors on it that I didn't like, and it's too long. And I've said that's all of them were too long, but this was the hardest one out of the 4 that we've seen. And I'm going to rate this test overall how hard it was. Now, two different ratings here. Ready? Someone who's strong in astronomy and tectonics, and then someone who's weak in those. Okay? So if you're strong in astronomy and tectonics, I would say this test for you was an 8.5 out of 10 hard. It's pretty hard. Like, very hard. This rating here is already, I think, basically as hard as the other ones. And those had every topic on it, or more array of topics. If you're weak in those 2 topics, this test is impossible for you. You probably failed, unfortunately. All right, so that's where we're at. I'm interested to hear your thoughts and opinions about what I said about all the questions. Thank you for tuning in, and there'd be a lot of content coming down the pipeline for everyone trying to get prepared for the August Regents, but this video in itself is a huge tool for you to prepare for August. Let me know what you thought in the comments below, and if you have any suggestions or opinions on what I thought about it, I'm very interested to hear about it. Good luck if you're retaking, and if you're not retaking, hopefully you did fine and you could at least check the questions you got wrong and compare with my video. All right, thanks for coming by. Good luck. Let me know what you think. See you later. Bye.